Okay, now let's do part 4.2, which is the root mean square current and the power for square waves. So work example 2, right? We'll be applying what we have learned in the previous part to square waves, right? So the key takeaway from previous part is you need to square the waves first, square the waveform first, take the mean, and then take the square root to find the root mean square current. So here in example 2, I present to you the following waveform, right? It is at current I1 for 3/4 of a period, and then it's get current I2, which is negative, right, for the next 1/4 of the period, and then after that the waveform repeats itself. Right, so we call this a periodic rectangular waveform. Okay. A, express the mean square current in the resistors in terms of I1 and I2. Part B, you're now given some values and you're asked to find the root mean square current. And lastly, you're asked to find the mean current. So let's look at A first. What is the mean square current in terms of I1 and I2? So if you look at the time between 0 to 3/4 period, the square of the current should be I1 square. And from 3/4 onwards to the final period T, right, it is I2 square. So if you then take the mean, right, since it's in 3/4 of the time is I1 and 1/4 of the time is I2 square, right? So I1 square for 3/4, I2 square for 1/4 time. The average would be the following equation, right? So 3I1 square plus 1I2 square divided by 4. Okay, so that's the mean. So if we do it graphically, right, what does it mean? Right, let's look at the graph. We square it. We get the following graphs, right, where I1 and I2 are squared. If you want to take the mean, right, it's as if you are finding the value of the red line. That means what is the value of the red line on the y-axis, where the areas above the graph is equal to the area beneath the graph, right? These two areas must be the same, right, for it to be the correct mean value. Okay, so I presented to you a mathematical way, but I also presented to you the graphical way. It is kind of important because later on you realize that you need the graphical method to understand the mathematical equations. Okay. Next, a lot of students always ask me, right? After because I've lectured AC for, I think this is my third time doing it, and of course I've revamped the notes a little bit, right? They ask me, what do you mean by taking mean? Is taking an average? So to give you an idea, right? If you look at this, if day 1 I give you 10 apples, day 2 I give you 5 apples, and day 3 I give you no apples, and then thereafter I repeat the structure or the number of apples I give every 3 days, you can see, right, here, let me take out my pen, that if I draw a line here, the area here would fit into this area here, right? And I think if you just follow the simple math, 10 plus times 1 plus 5 times 1 plus 0 times 1 and divide the whole thing by 3, you get the number 5, right? So the mean value of 5 that we know mathematically from our primary school math, right, can be represented, right, in a graphical manner as such. Then the next question that students ask after I present a simple example like that is that it's so simple, right? I can just do it mathematically. Why do I need to learn the graphical method? It's simply because there will be some harder ones where your mathematical methods don't work, right? Or you need the graphical interpretation to give you a better understanding. So in this case, a lot of students, I give the next example. For example, I give you 10 as apples the first day, 8 on the second day, then 5 on the third and fourth day, and 2 apples on the fifth day and none on the sixth day. Students will be tempted, right, to do 10 plus 8 plus 5 plus 2 plus 0 divided by 6. And they forget here that there is actually 2 days worth of 5 apples. Right? So if you're not careful, that could be a problem. So using a graphical method, then you will never have this issue, because you can see very clearly that, again, if you draw the line at 5, the area above the graph, above the line here, fits exactly into this area here. So the average is still 5. Okay, I hope I've literally painted a picture that is helping you understand what is taking the mean of a graph. Okay, right? We are asked that if you are given these values, what is the root mean square current? Right, so in the previous part, we found that IRMS is just the square root of the mean square current. And in part A, we found the mean square current to be given as this set of values, right? So we submit the values, we get 3 over 4 times 4 square plus 1 over 4 times 2 square, right? And you take a square root of the whole thing, you get 3.6 amperes, right? So now again, graphically, what does it mean? If you square it, you have taken the mean. Now you must take the mean value and you must square it back, and you find that it's actually 3.6. Take a look. It's a bit interesting, because see here, the peak value is 4. The value here is -2. The root mean square value is actually a lot higher than the mean value, right? If you don't believe me, let's look at part C, right? I put in part C to prove to you that the root mean square value and the mean values are not the same, right? If you want to take the mean value of the current, you will take 3 over 4 times I1 plus 1 over 4 times I2 divided by T, right? The full period. You'll find these values, you'll sub in the values, and you'll find that 3 over 4 times 4 is of just 3. 1 over 4 times -2 is -0.5, so you get plus 2 ampere. And you realize that this value in part C is not the same as a root mean square value. So if you had wrongly used the mean of the current squared times R to find the power, you have gotten the wrong answer. Right? You should use the root mean square current rather than the square of the mean current. Okay. With that, we have come to the end of 4.2.